So I'd like to provide an iterative solution for invert binary tree. And if you're not familiar with the problem statement, I encourage you to check that out. But really, the essence of the statement is that, if you have a binary tree, then really what you want to do for each node is you actually want it to, like right now, the left of 4, the root, is actually pointing to 2. You want it to sort of point to 7. And then for 4, you want it to point to 2. For the right pointer, you'd want it to point to 2. And the same could be said for each subtree. So, over here, you'd want it to point to 3. And over here, you'd want it to point to 1. So the right must point to the left must point to the right. And so on and so forth. So that's sort of the intuition behind the problem. And as far as the problem is actually concerned, we use a level order traversal. So if you're not familiar with a level order traversal, you essentially traverse each level, each node, but in a level-wise manner. So you're looking at 4, and then you move on to the next level, then you look at 2, then you look at 7. And so, a level order traversal usually makes use of a queue data structure underpinned by a linked list. And you begin by adding the root into the queue. And this is true in general for the level order traversal. You create a queue, and you add 4 to the queue, and so while it's not empty, while the queue is not empty, and of course it's not empty because you actually have an element there, you remove the element and then you add its children. So you've removed 4, now you add its children, which is 2 and 7, right? And then again, you repeat that process. You remove the element and then you add, children of 2, let's say 1 and 3. Or actually, rather, just to get this in level-wise format, you would have 4, and then you would remove it and then add 2 and 7, the children. And now that you have 2 and 7, now you'd move on to the next level, 1 and 3. So you can see if you were to do that, 1 and 3, right? If you were to print these while you're sort of taking them out, you can see we get a pattern here. It's 4, 2, 7, 1, 3, 4, 2, 7, 1, 3, right? So if you repeat this process, let's suppose we remove 7 now, and then we'll add 7's children, 6 and 9, right? You can see this entire 4, 2, 7, 1, 3, 6, 9 is actually, 4, 2, 7, 1, 3, 6, 9, right? So you can see that that's basically how the level order traversal works, but we're gearing this towards inverting the binary tree. So what we do here is while the queue is not empty, and of course it's not, as we said, there is a check to check if the root is null. If it's null, then we return null. Otherwise, we create a queue, and this is again piggybacking off of what the intention was in terms of level-wise traversal. We add the root, and then while the queue is not empty, and of course it wouldn't be empty since we've added the root, and of course if we've reached this point, then a root exists. We already checked if a root doesn't. We've added it to the queue, and now current will actually store. So current stores what we remove from the queue. So this remove API on queue actually not only removes it from the queue, but it also returns. If you were to look at the implementation for remove, it removes it from the queue, but it also returns the value that was removed. And so it stores it into current. And so right now, current is, we can say that current is equal to 4, right? And now the intention is to just say, we know, just given the implementation, each node has a left and right hand sort of. These are references, but you can think of them as hands. So 4's left is grabbing 2 and 4's right is grabbing 7. And the intention is to just say, current dot, current dot right will now just point to current dot left. And then current dot left will now point to current dot right. But the problem with doing that is that if you say current dot right points to, or current dot left points to current dot right, then when you say current dot right points to current dot left is pointing to current dot right. So you just basically be in a very tricky situation. Let me go over this again if it's confusing. If you say current dot left points to current dot right, and then you do current dot left or current dot right points to current dot left, you're not going to be taking this hand and moving this way, because as soon as you say current dot left points to current dot right, then when you say current dot right points to current dot left's pointing to the right here. So, you wouldn't get this motion. So in order to combat that, what you do is you store a temporary variable. So you say, okay, well, you're going to have a reference, one of these references, tree node called temp. And, this temp variable will store current dot left. So so you'll store current dot left before making the switch. So temp has a hold on this node here. And so you can safely do current dot left is current dot right. That's fine. But now when you say current dot right, you're not going to say current dot right is current dot left. Instead, you're going to say current dot right is temp, because temp had a handle there. And so so that's where this logic comes from. You have a grasp of the current, and then the temp will be just current dot left, right? Or temp will hold that left, and then the right will just be current dot right, like we said, will just be temp, point to temp. And then that's how you inspire the swap for, let's say one element. And this logic here just adds the children of an element. So, if the current dot left is a valid node, if it's not null, then you add it to the queue, right? So current dot right will you'll end up adding the right node. Let's see here. Yeah, if current dot right is not null, then you end up adding it to the queue. And if current dot left is not null, then you end up adding it to the queue, right? And now that you've added the children, you basically would come back up, and then, again, your queue is, certainly not empty, right? And remember that this current was actually removed up here. So this actually doesn't even belong in the queue anymore. But you've added the children, and now you repeat this process for these children now. Instead of doing this process once, where we would actually now be doing it for both 7 and 2. So you'd come back up again, you'd say, while the queue is not empty, and again, it's not, right? You have 2 present elements in the queue. Your current will now be 7. And so this whole process will now take place for 7. Current is now 7, and the current dot, the temp stores what is current. So temp is now 6. And then what you say in the code is that current dot, current is 7 here. So current dot left will now point to what's right. And then the right will end up pointing to temp, which is 6. And so you reversed it that way as well. And then, of course, eventually you stumble on 2 and you do it there. And even for these nodes down here, you actually end up doing it here as well, right? But null is null, so it's not even an issue, right? But that's essentially the working solution. And, it's fairly efficient with 81.74% efficiency and relative to, most of the solutions, although there are some higher ones there. But that's essentially the idea for this one.